The last speaker for the morning session is Emmanuel Hardy from CEA Leti. Emmanuel is a researcher at the Integrated Circuits for Power Management, Sensors and Actuators Lab. His interests lie in sensor data processing and circuits for tinyML. Emmanuel.
Hello. I guess you can hear me well. So today I'm going to introduce our system of end-to-end ultrasonic gesture recognition with pMUT sensors. So we drive an acoustic signal into a TX pMUT device. It creates an ultrasonic acoustic signal that bounces off an obstacle. So here it's a hand, a moving hand. Then we pick up this signal into an array of the same pMUT transducers. Each has an analog front end. Then we collect and aggregate all this data into a spike-based beamforming. And then we create features out of it. And then we do a gesture recognition using a spiking RNN, which gives us, after that, a class of the gesture. So the competing technologies for doing gesture recognition is infrared, electric field, radar, or camera. Our key advantages is that we are insensitive to light and shadow. With the MEMS transducer, we can be very low cost, and also, as I will try to show later, low power. So the key points I want to cover in this presentation is that to get an end-to-end power-efficient edge device, we need three things: so efficient sensors, analog to information conversion, and low-power inference. To build also such a system, you need quite a widely cross-functional team. So we have some MEMS design, IC design, lab measurements, data collection, training machine learning models, do some signal processing, prototype all this on PCB. So I want to thank the team for that, who brought all their domain knowledge into one system. So I'm going to present the work that's been published and presented at IEDM last December. So I'm going to start with a sensor array. So a pMUT is based on several hundreds of nanometers layers of material. So we have electrodes and aluminum nitride as a piezoelectric material. The specific structure has 5 electrodes, so it's called a bimorph. And we can use the same sensors for emitting ultrasound and for receiving by collecting the charges at the electrodes. So the resonance of this sensor is about 100 kilohertz. So we typically drive a single tone into those sensors, and so they need to be matched together, like between the TX and RX, and we can match them injecting a bit of DC voltage. And we manufacture this MEMS device on our 8-inch MEMS production line in CEA Leti. Here's our acoustic setup. So we have one membrane for emitting in all directions the ultrasonic signal. And then we got 2 arrays of 5 pMUTs, which are placed orthogonally to be able to do some 3D sensing. So the range we addressed with our prototypes is between 10 and 60 centimeters, but our prototype is fairly noisy. We think we can get maybe up to 1 meter, maybe 2, with better electronics, maybe better drive. So here's how our signal look. So we emit a short pulse of a few hundreds of microsecond pulse. Then there's a direct pass that goes straight from the TX to the RX that we need to ignore. And after that, we have a target echo with a specific phase shift and a time of arrival that's going to have all the information. So now I'm going to introduce our spike-based signal processing to do the beamforming. So when the sound arrives from a specific direction alpha, so the wavefront is going to be sensed by the array of sensors at different time. So this difference of time is dependent on the distance between each element. So we have 1.5 millimeter pitch. The sinus of the direction of arrival divided by the speed of sound. So to be able to sense this different time of arrival, what we do, so we have a sine wave. So by measuring the phase difference between each channel, we can measure this time. So we decide to compress the signal. So instead of converting to digital the whole signal, we just remove the noise with a bandpass filter. Then we have a comparator, and we keep just the rising edge. So it means that each channel is now converted to a single bit with a sampling frequency of like 4 megahertz in our example, which gives us plenty of resolution. So now to get like the direction information, like we do coherence detection. So by applying the theoretical delays for several possible direction of arrival. So here I have the direction 0 degrees. So 0 degrees, it doesn't have any delay between the sensors. But since the sound is coming from another direction, we see that the signals are not in phase. So the spikes are actually not in phase. So we don't detect any coherence. Since the sound comes from direction alpha, like we create a channel where we apply the theoretical delay corresponding to that direction. So now we have the spikes. The spikes are in phase. So we detect that simply by counting the number of pulses within a window after a delay line. And if this count passes a threshold, like we emit a coherent spike. So we replicated this processing in 11 directions. So we get plus or minus 50 degrees range with 10 degree steps. And the surprise is that with optimal threshold and window size, we get really, really good definition of the beams and with no artifact. So if we compare this to conventional delay and sum beamforming, we see that we have about 3 times better angular sensitivity at 0 degrees, like no side lobes, and we get also increased angular range because delay and sums doesn't work very well at 50 degrees. The downside is that it's not a linear operation, so once you get a bit further, like you don't get the spike count that passes the threshold and you stop seeing anything, whereas a conventional beamforming is gonna work like possibly like further range. So now how we assemble our feature vector. So for each line of pMUT, so we have 2 arrays. For each line we have a y direction and an x direction. We get a coherence matrix. So on the x-axis is actually the time of flight, and the y-axis like the different beamforming beams. We decide to aggregate all this data into a 2-direction vector, so by just summing over the distances. Then if we sum over the direction, we get a distance vector, and we obtain a small 35 vector. So we could do a gesture detection on a full matrices with 286 dots. But actually, by aggregating and simplifying our matrix, like we really simplify the calculation of the feature. It's less work for the neural net, and we get decent detection for the gesture, and it's also simpler training. I'm gonna give you 2 examples of gesture to give you a sense of what it looks like. So here we see that on the x-axis, like we see the angle shifting slowly, not changing much on the y-axis, and we see a bit of distance movement on the distance. So that's a left-right gesture. Here we see mostly on the bottom like an obstacle coming far and closer to the sensor and then back. So that's a push-pull. So like here we can roughly guess like which type of gesture it is from just looking at the feature map. So it gives us confidence that with a simple neural network we should be able to make decent prediction. So for that we wanted something really efficient. So we chose a recurrent neural network type of network. So because it has like trainable temporal dependency. Doesn't have a fixed window, so we could support like various lengths of gesture, and also is very computationally efficient. You don't need to buffer much data, like you just have this state that you update at each new feature. We worked on 2 classifiers. So first a baseline, because we collected our own data set, so it's always useful to have like a floating point baseline to do some quality control, like try to figure out what's a good loss function, data set balance, and so on. And then our hardware target, it's a Spiking Recurrent Neural Network that got implemented onto an ASIC. So it has 110 features, but it's simply it just have a simple recurrence, so it's not a gated recurrent network such as GRU. So I'm going to show a bit like what we implemented in terms of Spiking Recurrent Neural Network. So x of t is the number of spikes per frame. It's an integer number. Y of t is the output spikes. So it's working at the frame rate, so which is I think 25 Hertz in this case. So very slow update of the temporal mechanisms. V is a state that we update at each frame, and y of t minus 1 is a previous state. So we have 4 temporal mechanisms. So we have a synaptic delay, then we have a leakage time constant, then once the membrane potential reaches a threshold, we fire a spike, and after that we have refractory period where we ignore the subsequent spike. So it's all hyperparameters of the network. So here I'm showing like the output of the network after a gesture. So we've done a bit more quantization of the feature, because what really matters is really the trace of the gesture. And we can see that in a streaming fashion, like towards the end of the gesture, the probability increase, and then it decreases to get ready for another classification. So it shows like a streaming behavior. Here's our setup. So I presented like a mixed signal approach without any ADC. But to be able to develop this system and try out the signal processing, we developed a prototype like with our pMUT, discrete electronics for the analog front end, then converters that we use like to collect all the data. Then we implemented on an FPGA the bandpass filter and the current edge detection, plus after that all in digital the spike-based beamforming to communicate with the Spiking Recurrent Neural Network ASIC. Here's our gesture data set. So we have 5 simple movements, like 4 swipes plus this push-pull gesture, plus a non-class, which is really useful. Collected 500 examples from 12 participants with 10 to 50 centimeters distance to get a bit of variability. And we use data augmentation for training, like taking advantage of the system symmetry. Like you can easily transform a right-left into upwards or left-right by recombining the data from the different sensors. So in terms of classification, like on these 5 classes, we get like about between 85–90% accuracy. So it shows that it works. It's far from being perfect. We show also like only a small drop from the GRU implementation to the SRNN. Some movements are a bit more difficult to detect than others. So we can see there's a bit of gesture ambiguity for some of them. It could do too many things, like we have quite small data set. There's also ambiguity between the gesture, because people don't do gesture just orthogonally. So yeah, but we show basic functionality. I want here to finish this presentation by comparing our work with the state of the art to really make my point about how much energy saving we can get from using such an approach. So in terms of classification accuracy, so there are many systems, many data sets, different conditions, so you cannot really compare apple to apples the accuracy. I want to really compare between those two systems. So on the Bjebela paper from 2015, it's fairly similar to our approach. So they have a pMUT array on silicon with a bunch of ADCs for each channel, a bit of signal processing, and then they do just obstacle detection, not gesture recognition, but it's fairly similar. But they've done the full integration into an ASIC. What we've done is, based on our knowledge of ASIC design, we've done an estimation of how much power our approach would take. So here we divided the power consumption into 4 categories. So how much energy we use for driving the ultrasound. So it's based a lot on the sensors, like the frequency, what the capacitance of your sensor. So that depends system to system. The interesting one is the analog part. So in this other system, they have a full ADC, so they're running around 200 kilohertz. So they have bandpass delta sigma. For each channel, it burns a lot of power. For us, we don't have really conventional ADC. So we get our data, we have an analog bandpass filter, a comparator, and then we get just 1 bit data. So it's a lot more efficient in terms of power, like 3-4 orders of magnitude for that one. Same in a digital processing, so instead of running on a 12-bit data, we just combine 1 bit stream, so it's almost nothing in terms of hardware. So ours is post-synthesis power estimation. And then for classification, so they don't have classification, I just want to show that we use an event-based inference. So it means that when there's nothing much happening, there's no event, so we consume less power. And when there's a gesture, there's some more activity. So we can see that we burn power when it's useful. Okay, so to wrap up, some applications. So gesture recognition, that can be used for wearables, automotive, VR headset. Something that would be, I think that would be a really cool application for this technology would be obstacle detection. So if you remove all the gesture detection part, if you look at the features that we get on the output of the spike beamforming, you actually see a map of the obstacles, with range and angle of arrival. So you could do a very cheap but very low power obstacle detection. You could also further improve the system by focusing the beam in different directions, so do also beamforming at emission. So what's next for us is to try to apply this approach to new sensors from CEA Leti, because we do lots of MEMS design. We're building lots of different types of sensors, and then try to build new prototypes and ASICs. So the takeaway point is with a small, we've shown a system with a small form factor pMUT array. So that's thanks to the MEMS process, we can produce them at low cost and at a large scale. So beamforming and signal processing in a spike domain that enables super low power operation because it doesn't have a conventional ADC. And then low power gesture classification that relies on the event nature of our data. And so I'd like to finish here by emphasizing again that an analog to information strategy, like co-optimize with the whole system, can really yield more efficient sensors and edge AI systems. Okay, thank you very much.
Thank you, Emmanuel.